So, Jain to all, this is lecture 5 of subject signal system KC 403, and the topic is inverse jet transform. I am Dr. Amit Garg, Associate Professor in EC Department of AKGEC. So, in this particular lecture, we will see the different techniques by which we can take the inverse jet transform if the jet transform is given to us. So, in my previous lecture, I have covered what is jet transform and how can we apply jet transform to obtain the jet transform of a discrete time signal. Now we will see how to again obtain the discrete time signal using the jet transform. So let us start with the inverse jet transform. So inverse jet transform of xz is basically given by this expression, which is xn equals to 1 upon 2 pi j, and this is closed contour xz into z to the power minus 1 dz. So this is the expression which is generally used to find out the inverse jet transform, but this is basically, you can see this is the complicated integration formula. So we are having some different techniques also by which we can find out the inverse jet transform without using this particular formula. So we can see there are 3 methods that are used for the evaluation of inverse jet transform. First method is contour integration method. It is also called residue method because in this particular method we are using Cauchy's residue method. Cauchy's residue theorem. So that's why this method is also called residue method. So first one is contour integration method, which uses this particular formula for finding out the inverse jet transform. Okay. Then another method is you can say the long division method or power series expansion method. So this method is generally used whenever we are interested only in finding out some values of the jet transform near the origin, you can say, because the disadvantage of this method is that you will not get the closed form solution. You will get the open solution. You will not get the closed form solution. But analytically, it is easier to find out the solution. That's why we are using this method. And for this particular method, we can only find out the signal in one direction, either in right direction or in left direction. Means for non-causal type of signals, we cannot apply this long division method. Then third one is the most appropriate or popular method, that is the partial fraction expansion method. So in which what we will do, basically we will take the jet transform, we are having the jet transform, we will take the partial fraction, and after doing the partial fraction, ROC is also given to us. So based on ROC, we will find out the inverse jet transform of the obtained functions after partial fraction. So let us start with the contour integration method. So inverse jet transform is formally given by this formula, where the integral is a contour integral. Okay, so this is a contour integral over a closed path C. So you can say this is your closed path C, and on this particular path, so where the integral is a contour integral over a closed path C. So let us suppose this is our closed path C that encloses the origin and lies within the region of convergence. So you can say this is, let's say, upon this is our origin. So this contour integral basically should enclose the origin and lies. This should enclose the origin and also lies within the region of convergence of xz. Okay. So based on that, we will choose this particular circle and we will take the closed path C according to that. This is based on the ROC. So the contour is what? It is any circle of radius r in the region of convergence. So you can say you have taken this circle, let's say, so this is the radius of this circle. Okay. Now because we will use residues in it. So what is residue? The contour integral can be evaluated using standard techniques from complex variable theory. So there is a theorem due to Cauchy which says that if fz is single valued and analytic on and inside a closed path contour C, except for a finite number of poles P1, P2, Pn inside C, then you can find out this xn according to this formula, and that will be equal to k equals to 1 to n rk, where r is the residue due to a single pole, and rk means if we are having k number of poles, so for each and every pole we will find out the residue value, and the sum of the residue value will give us the inverse jet transform. Okay. What is this Cauchy theorem? Fz is single valued analytic. Analytic means there is no discontinuity on it. Means for each and every value you will find that the function is analytic, means the function is finite at all these values except at poles, because at poles you know the value is infinity. Okay, so you can say xz does not converge over there. Okay, so this is you can say so you can see here is a closed contour C except for a finite number of poles. Okay, inside C. So we have to take only those poles according to ROC. This ROC is defined in terms of you can say mod z is greater than mod z r. Means you can say this ROC is according to the ROC defined. We will take a circle of which is defined as C, and according to that we will find that which poles are lying within this circle. Only those poles are used for finding out the residues. Okay, so xn is residues of xz into z to the power n minus 1. Why we have taken xz into z to the power n minus 1? Because fz, which is analytic, is defined as xz into z to the power n minus 1 according to Cauchy's. Okay, so we will find out, rather than finding out for xz function, we will find out the residue for xz into z to the power n minus 1. So you can see here xn, which is inverse z transform, is nothing but the summation of all poles of xz which are lying under this circle C. For those we will find out the residues. And how we will find out the residue? So residues can be find out using these formulas, where the residue for a pole of order m at z equals to alpha is. So this is the formula based on which we can find out the residue. Okay, and m is the order. Means let us suppose we are having two poles. One is, let's say, z equals to 0.5, another one is, let's say, z equals to 0.7. So in this case, this pole is also of order 1 and this is also of order 1. But if let us suppose we are having equation where the poles are z equals to 0.5 and 0.5 both, in that case the order is 2. For this particular pole order is 1, but this particular pole order is 2. So if let us suppose we are having all the poles which are occurring only once, so you can say the value of m will become 1. Okay, so according to this formula, this is 1 upon factorial m minus 1. So this is 1 upon factorial 0. So you will get value 1. Limit z tends to alpha. Alpha is the pole. So let's say z equals to 0.5 is the pole. So you will find the limit z tends to 0.5. Then dm minus 1 upon dz m to the m minus 1. So this is again 0. It means we will not take the differentiation. And this is also 1. So you will get, for a single pole, you will get the equation for finding out the residue is limit z tends to alpha, z minus alpha, xz into z to the power n minus 1. Okay. So, and for order 2, if let us suppose our pole is lying at 0.5 2 times. So in that case, this is 1 upon factorial 2 minus 1, it means 1 upon factorial 1, it means again 1, limit z tends to 0.5, but here you will find m is 2. So this is d by dz of z minus alpha to the power 2, xz into z to the power n minus 1. So accordingly we will find out the poles, we will find out the residues for the poles. Okay. So now we will see one of the problem based on residue method. So here we have find out the inverse Z transform using the contour integration method or residue method. And ROC which is specified us is mod Z greater than 0.5. Okay. So let's see the solution. So we are having an analytic function, let's say, which we have taken as fz previously, is x naught z equals to xz into z to the power n minus 1, and z to the xz is given as 1 upon z minus 0.25 into z minus 0.5. So you can say this is xz into z to the power minus 1 can be written like this. Now for convenience, what we can do, we z to the power n into z to the power minus 1. And z to the power minus 1 we are taking in the denominator side. So we are having these three poles. Three poles are lying at z equals to 0, 0.25 and 0.5. And here ROC is any circle which is greater than mod z is equal to R, which is greater than 0.5. So if ROC is given like this, it means all these three poles are lying inside this contour, inside this closed circle C. Okay, it means we have to find out the residue for all these three poles. For all these three poles, because ROC, this circle consists all of these three poles. If let us suppose ROC is greater than, mod Z is less than, greater than 0.5 and less than 0.5, let us suppose ROC, if for your understanding, I am just telling you, let's say ROC is somewhat like this. Okay, then in that case, you will not include this pole for calculating the residue. But ROC, if is given like this, then in that case, you have to find out the ROC, find out the residue corresponding to each and every pole. Okay, so the residue method, according to residue method, your action will become residue x naught z at z equals to 0, residue x naught z at z equals to 0.5 and residue x naught z at z equals to 0.5. So here x naught z and fz is same, you can say. Now we will find out the residue of x naught z at z equals to 0, at z equals to 0. So at z equals to 0, we will see what is the value of x naught z here, z to the power n minus 1 upon z minus 0.25 into z to the power z minus 0.5. So what happened? What happened if we have seen the case, this is the formula, according to this formula, how we will get this term? This term is basically z minus 0, because pole at z equals to 0, multiply by z to the power n minus 1 upon z minus 0.25 into z minus 0.5. So that's why it is written like z to the power n here. Okay. So this is at z equals to 0.5 and this is at z equals to 0.25 and this is at z equals to 0. So you can see in each and every case what happened, z minus alpha term will be there. Okay. So you can see the terms you are getting here is like this. Now for pole at z equals to 0, residue is z times x naught z, which we have seen here. So z times x naught z at z equals to 0. So you will get this equation, you will multiply by z, so you will get this equation, and now put z equals to 0 in it. So you will get the residue corresponding to pole z equals to 0 is 0. Next, we will see the residue due to z equals to 0.25. So you can see here z will be equal to 0.25 and here the term z minus 0.25 will be there and multiply by x naught z. So x naught z is your z to the power x naught z is your z to the power n upon z times z minus 0.25 into z minus 0.5, and when you will solve it, you will get the value minus 16 1 by 4 to the power n. Okay, this is for pole z equals to 0.25 and this, and for z equals to 0.5 again your equation will be like this, and we are getting the term 8 into 1 by 2 to the power n. Now we will sum all these a, b, c residue values. Okay, so when we will add up all these values, so we will find out the solution, this 8 into 1 by 2 to the power n minus 16 1 by 4 to the power n un. Why we are taking un? Because mod z is greater than 0.5 and you can say the ROC is outward. So that's why this ROC is outward means your signal is causal signal. So you will get the causal signal corresponding to both of the poles. So that's why un is also here. Okay. So this is your Cauchy residue method. Important thing is that we have to take only those poles which are enclosed by the circle C, and that circle is defined based on the ROC given to you. Okay. Now next is power series expansion method or long division method. So in this case, you know the formula for Z transform. This is like this. So if you will expand it, you will get the negative powers, positive powers of Z first of all, then you will get the value at x at n equals to 0, and then you will get the positive values of xn and negative values of z. Okay. So given a Z transform xz with its corresponding ROC, we can express xz as a power series in z to the power minus 1 or z of the form defined in the above equation. The values of the signal xn are then given by the coefficient associated with z to the power minus n. This inversion method is suitable to signals that are one-sided, that is discrete time signals with ROCs of the form mod z is less than alpha or mod z is less than greater than alpha. However, long division method got lead to a closed form expression. So these are things I have, I think, already explained in the introduction part. Okay. Now we will see one of the numerical based on this long division method. So we have given this method. So first of all, mod z is greater than 1 means we are expecting a causal type of solution. Means your Xn signal will be a causal signal. Okay. So in this case, we require negative powers of z. So we will take these two terms like this and divide. We will take these terms like this, and this is your basically numerator, and you will divide. So first of all, you will try to cancel it. So you will take first one value 1. So you will get 1 minus 3 by 2 z to the power minus 1 plus 1 by 2 z to the power minus 2. Then it will be cancelled out, and you will get this term 3 by 2 z to the power minus 1 minus 1 by 2 z to the power minus 2. So for satisfying 3 by 2 z to the power minus 1, you have to put 3 by 2 z to the power minus 1 here. Again, it will be cancelled out, then you will get this term. Then according to this term, we will take the value 7 by 4 z to the power minus 2. You will take plus the sign because here is plus sign, and when both are plus, then only then it will be cancelled out. So after it, you will get this term, and later on you will get this term. So it will be, you are getting the negative powers of z as you will go on. Okay. So that's why these are the values of xz. Okay, these are the values of xz. So based on these values, we can define our signal because it is causal signal. So xn will become, so xz is this, so xn will become 1, 3 by 2, 7 by 4, 15 by 8, 13, 31 by 16, and you have to put dot 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 at the end. So this is our sequence. Okay, and similarly, if for this particular question, if ROC is mod z less than 1 by 2, means we are expecting a solution in which signals are non-causal signals. So signals are non-causal signals. Oh, sorry, signals are anti-causal signals. Okay. So you are expecting positive powers of z. So how you will get the positive powers of z? You will write the same term, but you will write negative powers first, and then you will go in this direction. And this one is there. And now you are expecting positive powers of z, so that you will try to cancel out this term. So you have to take 2z square first value, so that after this multiplying it, remainder is this. Then you will take this value, so that you will get this remainder, and like this. So you are having solution in positive powers of z, you can see here. Okay. And so xz will become 2z square plus 6z cube plus 14z, and like this. And if you will write it in terms of sequence xn, because all are positive powers of z, so you will see that there is no power of z, and there is no power of any constant value z to the power 0. So you can see this term is 0, this term is 0, and 2, 6, 4, 14, 30, 62. Like this you will write, and it will become up to so an infinity. Okay. So you are getting the solution in left direction in this case. Okay. Now come to the third method, which is partial fraction method. So generally we are interested in finding a general expression rather than the expression in which we are getting only the positive powers or negative powers. So we are using this partial fraction method. Okay. So to find the general expression, we can use partial fraction expansion and known inverse Z transform pairs of low degree rational functions. Okay. It means we will see this also using a numerical. Here you can see the xz that is given to you is 3z to the power minus 1 upon 1 minus z to the power minus 1 upon 1 minus 2z to the power minus 1. And different ROCs are given to you. Different ROCs are given to you. Okay. One important thing that I want to discuss here is, first of all, what we will do, we will convert this into positive powers of z. Okay. So what we will do, we will multiply by, if we will multiply by z square in numerator and denominator, so this will become 3z, and 1z is multiplied here and 1z is multiplied here in denominator, so it will become z minus 1 upon z minus 2. Okay. And then because you know here the situation is that the term is 3z upon z minus 1, z minus 2, but what you will do, you will take this z here. So xz by z will become 3 upon z minus 1, z minus 2. Okay. Now you will do the partial fraction. You will do the partial fraction for this term, and later on you will multiply by z. So after doing the partial fraction, we are having this type of term after the partial fraction. Again we have divided by z in numerator and denominator both sides. So we are getting 1 upon 1 minus z to the power minus 1, and here 1 upon 1 minus 2z to the power minus 1. Okay. And here ROC is mod z is greater than 2. So here you can see where are the poles located here at z equals to 1 and at z equals to 2. There are two poles at z equals to 1 and another one is at z equals to 2. So you can see ROC is outside the outermost pole is 2. So you can say for both the poles, the corresponding term will give the solution corresponding to a causal signal. Okay. So according to causal signal, we will write it like 1 upon 1 minus z to the power minus 1 is minus 3 un plus 3 into 2 to the power n un. 2 to the power n un is nothing but 1 upon 1 minus 2 z to the power minus 1. So this is the solution when mod z is greater than 2. It means both the signals must be causal. Second, mod z is less than 1. Mod z is less than 1 means ROC is inside the innermost pole or leftmost pole. So for this particular case, solution corresponding to this both these poles must be anti-causal. So both signals must be anti-causal. So that's why you will get the inverse Z transform for anti-causal signal is minus of 1 upon 1 minus A Z inverse is 3u of minus n minus 1, and here minus 3 2 to the power n u of minus n minus 1. Okay. For this ROC you are getting this. And third one is when ROC is lying between 1 and 2. So you are having a circle of radius 1, you are having a circle of radius 2, let's say a 1 and this is 2. So you are talking about this term. So you are getting this ROC only when corresponding to 1 we are having ROC outside and corresponding to ROC is inside. So corresponding to pole Z equals to 1 we are having causal solution, and corresponding to pole Z equals to 2 we are having anti-causal solution. Okay. So you can see this is written Z equals to 1 must be causal and second signal pole Z equals to must be anti-causal. So the solution is minus 3 un and here minus 3 to the power n u of minus n minus 1. So this is how you can basically calculate the inverse Z transform using partial fraction method. And here we can see the poles are located at Z equals to 1 and Z equals to 2. Okay. Important thing is that this Z is you can take this Z as it is, but this Z is not basically positive power Z. So this is 0. So 0 will not affect anything on this aspect. Okay. Now solving a difference equation using the unilateral Z transform, like in case of Laplace transform, we have solved the equations. We can also solve the difference equation here using the Z transform. Important thing is that in case of difference equation, we will take only unilateral Z transform. Unilateral Z transform means we are only interested in causal type of solution. Okay. And what happened when we will apply Z transform to any difference equation, then we will get the algebraic equation, and then that algebraic equation can be easily solved. Okay. So based on this, if we will see there are two types of output. One is zero input response and another one is zero state response. So zero input response is the response when you are not applying any input to the system and you are getting the response, and that response is due to the initial condition of the system. Okay. And zero state response means your output is only due to the input applied to the system and there are no output due to the initial condition of the system. But if you will talk about the total response, then total response is zero input response plus zero state response. Zero input response is due to initial conditions, that's why it is called natural response, and zero state response is due to the applying any input, so that's why it is called forced response. Now we can see one of the questions based on this. So we have given our difference equation. You can see this is our difference equation where yn is the output, xn is the input, and input xn is given as 2 to the power n un, and with initial condition y minus 2 equals to 0 and y minus 1 equals to 5. So because xn is given as 2 to the power n un, so we will find xz, that will become z upon z minus 2. a to the power n un 1 upon 1 minus a z inverse or z upon z minus a. Okay. Now we will take this equation. Now taking the z transform of the equation both sides, yn corresponding to yn, we will get the term yz, and for yn minus 1 we are having the z transform z to the power minus 1 yz plus y of minus 1, because initial conditions are given and we are finding out the response. If we are finding out the transfer function, in that case we will assume all these initial conditions should be 0, but because we are finding out the response, so that's why we have to take these initial values. Similarly, for this term minus 3, the z transform of yn minus 2 is z to the power minus 2 yz plus z to the power minus 1 y minus 1 plus y minus 2. And similarly here xz plus 4 z to the power minus xz plus x of minus 1. Okay. This is written over here. You know, these are the initial conditions. Okay. So now we will substitute all these values here. So you can see here minus 2 y minus 1 is 5. So you will get this term 10. And again we will put this initial conditions over here, and while solving it, finally we will get the expression somewhat in this form: yz times z minus 3 times z plus 1 upon z square. So this, while solving is, you will get this. Okay. So yz, now you have to take yz, you have to take the inverse z transform of yz to obtain yn. So yz you have written finally in this form. Now you can take the partial fraction, but important thing is that you cannot take the partial fraction for this term because the order of numerator and denominator both is same. So you cannot apply z transform. So rather than taking yz, we will take the value of yz by z. So that you will get this term. Now you will take the partial fraction for this term, and after partial fraction you are having values. You can represent it like this ABC, and while calculating this value, A and B and C are minus 4, 33 and 33 by 2 and minus 3 by 2. Okay. So you are putting this value here, and then you can solve it like this. So yz is this, and again divide by z in numerator and denominator. So you are getting this type of term. Okay. And if you will take, now important thing is that you are taking unilateral z transform. So only causal powers so your signal is causal only. Okay. It means we are only interested in negative powers of z. Okay. So according to that, minus 4, this is 2 to the power n un, 32 by 2, 3 to the power n un, and minus 3 by 2, minus 1 to the power n un. Means here there is no ROC sort of given, because ROC is not required in unilateral type of solution. Okay. So final solution is this. Here you can see un is written. Because unilateral z transform is only applicable for the values n values from 0 to infinity. For minus infinity to 0, that is not applicable. Okay. And so these are the references you can see, and thanks for your kind cooperation. Thank you so much.